Welcome back to the deep dive. Today we're attempting something a little bit dangerous.
It's dangerous.
Well, not physically dangerous. We're perfectly safe here. But intellectually, it's a bit risky.
Oh.
Usually, we take one specific thing, a person, a single event, a book, and we just drill down on it.
Right, the deep dive.
Exactly. But today, we're doing the opposite. We're zooming out, way, way out. We are trying to tackle the entire timeline of space exploration in one sitting.
It's a significant undertaking, to put it mildly. We're trying to compress, 400 years of physics and engineering?
And just sheer human audacity.
Sheer audacity, yes,
Yeah.
into a single conversation. It's a lot.
It is. And honestly, when I first started looking at the source material for this, all these, endless lists of dates and mission acronyms, launch weights, my eyes glazed over a bit.
I can imagine.
I thought, okay, this is going to be dry. This is going to be a lecture. But then I started reading through the notes you put together, and the whole narrative just shifted for me. This isn't a list. It's a story. It's a story about acceleration.
That is the word. Acceleration. That's the key.
It really is. It's a story of how we went from, Galileo looking at Jupiter through a tiny tube in 1610 to October 2024, where we watched a giant mechanical tower literally catch a 20-story rocket booster out of the sky.
It's science fiction made real.
It is. And since today is Tuesday, January 20th, 2026, we have this incredible vantage point, right? We can look back at the last century of this, but we can also look back at just the last, say, 12 to 18 months, which, they've been some of the most sci-fi months in all of human history.
They absolutely have. But I think the mistake people often make, and this is why doing a timeline like this is so important, is thinking that something like the Chopsticks catch of the Starship booster, or even the Fram 2 polar mission, that they just happened in a vacuum.
Right, that they came out of nowhere.
They didn't. They are the cumulative result of centuries of pressure, of work. If you actually look at the timeline, you see these really long periods of, theoretical gestation.
People just doing math.
Literally people doing math by candlelight.
Oh.
And then suddenly a barrier in the physics is overcome, and the milestones start flying by at a rate that, honestly, the human brain kind of struggles to process.
So that's our mission today, to trace that exact arc. To understand why we're living in what feels like a new golden age of spaceflight right now, we have to go back and understand the dreamer age that started it all.
We have to go back to the math.
The dreamers and the math, that's our first segment. So the timeline technically starts in 1610 with Galileo, but why there? People have been looking at the stars forever.
True. But 1610 marks the shift from just looking to observing. It's a crucial distinction.
Okay.
Before Galileo, astronomy was, a naked eye science. It was mythology, it was navigation, calendars, all important stuff. But
It was flat.
in a sense, yeah. Then Galileo gets his hands on a telescope, which was a pretty new invention at the time, and he points it at Jupiter. And he sees moons orbiting it. He points it at Venus and sees phases, like our moon has, which proves it orbits the sun.
Ah, so suddenly the sky isn't just a dome with lights tacked onto it?
Exactly. It's a place. It has depth. There are other worlds out there that are in some ways like our own.
It changes the definition of universe from a painting into a landscape.
A perfect way to put it.
Yeah.
But the real tragedy of that era was the enormous gap between vision and capability.
We could see it, but we couldn't touch it.
We were firmly stuck at the bottom of Earth's gravity well. And this is where, looking at the timeline gets a little frustrating. There's this huge gap. You have William Moore in 1813 talking about the rocket equation based on Newton's laws. But the date that really stopped me in your notes, and I had to double check it because it just seems impossible, was 1903. Konstantin Tsiolkovsky.
The father of cosmonautics.
Right, but think about what 1903 is famous for in most history books.
Kitty Hawk. The Wright brothers.
Exactly, the first powered airplane flight.
Yeah, a couple of guys on a sand dune in North Carolina flying what was basically a glorified kite with a lawnmower engine for, 12 seconds?
12 seconds, barely hopping over the sand. But you have to understand, while the Wright brothers were doing that, Tsiolkovsky was in Russia, sitting in a log cabin, proving with mathematics that spaceflight was theoretically possible.
In a log cabin.
Yes. He was a provincial school teacher in a town called Kaluga. He lived in a wooden house. He'd been almost entirely deaf since he was a child from scarlet fever, so he was very socially isolated. And in that isolation, in 1903, he published a paper called Exploration of the Universe with Rocket-Propelled Vehicles.
Wow.
He wasn't building hardware. He was building the entire mental framework for space travel.
So while the rest of the world was just marveling that a human could fly maybe 10 feet off the ground, this guy was basically designing the Saturn V in his head.
Essentially, yes. He laid out what we now call the Tsiolkovsky rocket equation. And without getting too bogged down in the calculus, it's the formula that connects how fast you can go, your change in velocity, to the mass of your fuel and the speed of your exhaust.
And that's still what we use.
That equation is still the tyrant of rocket science today. Every single mission planner at NASA, at SpaceX, at Blue Origin in 2026 still has to bow to Tsiolkovsky's equation. It dictates everything.
And he got specific too, right? He wasn't just saying, make a big fire and go up.
Oh, he was incredibly specific.
Yeah.
He proposed using liquid oxygen and liquid hydrogen as propellants.
Which is?
The exact fuel mix used on the space shuttle's main engines almost a century later. He proposed staging, the idea that you should drop off your empty fuel tanks as you go to get lighter and go faster.
It's mind-blowing. He's living in a world of steam engines and horses, and he's visualizing multi-stage, liquid-fueled rockets.
It gets even crazier. In 1895, after seeing the Eiffel Tower, he conceptualized the space elevator. He was a man literally living in the future, just waiting for the metallurgy to catch up to his ideas.
And it took a while for the hardware to catch up. We don't see the first liquid-fueled rocket until 1926 with Robert Goddard in the U.S., and that wasn't exactly a moon rocket.
Not at all. It was about the size of a coat rack. It flew for 2.5 seconds, got about 41 feet up the height of a 2-story house, and landed in a cabbage patch.
A cabbage patch.
But it proved the chemistry worked. It was the proof of concept. Tsiolkovsky's math was valid. You could, in fact, use liquid fuel to generate stable thrust.
Okay, so then we hit the 1940s, and the story gets a lot darker. We can't really talk about the history of space exploration without talking about 1944 and the V2 rocket.
We can't. It's the uncomfortable origin story of the entire space age. We like to think of space exploration as this noble, Star Trek-style quest for knowledge. But the very first human-made object to cross the Kármán line, the accepted boundary of space, 100 kilometers up, it wasn't an explorer's probe. It was a ballistic missile. The German V2 launched in June 1944.
It's such a jarring duality. The same technology that eventually took Neil Armstrong to the moon was born directly from a desire to destroy cities like London and Antwerp.
It is the great paradox of rocketry. Wernher von Braun and his team, they developed this incredible technology for the Nazi war machine. After the war, Operation Paperclip brought those engineers and their hardware to the U.S., while the Soviets captured other German scientists and facilities. The V2 literally became the biological parent of both the American Redstone rockets and the Soviet R-7s.
So the family tree of every rocket we see launched today has this very dark root.
It does.
Speaking of those early tests in the U.S. after the war with the captured V2s, I found a detail in the notes that I just absolutely love. We always hear about the monkeys, we hear about the dogs, but the actual first astronauts, the first living things to survive spaceflight, were fruit flies.
That's right, 1947. A captured V2 rocket launched by the U.S. from White Sands, New Mexico. On board was a capsule full of fruit flies.
But why fruit flies?
To study radiation.
Yeah.
That was the big unknown. Nobody had any idea if cosmic rays at that altitude would instantly kill living cells or cause horrible mutations. The flies went up, crossed the line of space, the capsule came down by parachute, and they were alive.
Wow.
Sounds so trivial now, but that was the fundamental proof of concept for biological survival at the edge of the vacuum.
And it wasn't until 1949 that we sent the first primate, Albert II, a rhesus monkey,
who tragically died on impact. The parachute failed.
Yeah.
The early days were incredibly brutal. So many failures.
Right. And then, of course, the most famous one, Laika the dog in 1957. But Laika represents a huge jump in difficulty, doesn't she?
A massive jump. Laika was on Sputnik 2. She was the first mammal in orbit. And we really need to clarify that difference for anyone listening because it's a distinction that comes up again and again.
Suborbital versus orbital.
Correct. Going to space suborbital flight is basically going straight up and falling back down. It takes a lot of energy, but it's manageable. Orbiting.
Yeah.
That means you have to go sideways so incredibly fast, about 28,000 kilometers per hour, that as you fall towards the Earth, you miss it.
You're constantly falling over the horizon.
Precisely. And that is an entirely different beast of physics. It requires exponentially more power.
Which brings us to the starter pistol, segment 2, the sprint. 1957 to 1969, the era everyone knows, or at least thinks they know.
The space race proper.
And it all kicks off with Sputnik 1, October 4th, 1957, that little beep, 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 heard around the world.
The psychological impact of Sputnik is almost impossible for us to grasp today. We're surrounded by satellites. You can look up and see Starlink constellations blanketing the sky.
It's routine.
But in 1957, the sky was empty. It was pristine. Then all of a sudden, there was a Soviet sphere flying over the United States every 90 minutes. It absolutely terrified the West, but it galvanized the species. It turned space from a theoretical playground for scientists into a geopolitical imperative.
And looking at the timeline from that point on, the acceleration is it's bonkers. I want to zoom in on 1 year, 1959, because in the popular history, we tend to skip from Sputnik straight to Gagarin. But 1959 was an absolute barrage of Soviet firsts.
It was the year of the Lunas, an incredible series of missions.
Yeah.
In January 59, Luna 1 becomes the first spacecraft to reach escape velocity.
Meaning it broke free of Earth's gravity entirely.
Correct. It went so fast it just kept going. It actually missed the moon, which was its original target, but in doing so, it became the first artificial planet orbiting the sun.
And then Luna 2?
September 1959. Luna 2 slams directly into the moon. It didn't land softly, it crashed.
Oh, yeah.
But that was the whole point. It was the first time humanity physically touched another celestial body.
And then just a month after that, Luna 3.
Luna 3 flies around the moon, and on board, it has a little automated film developing lab. It takes pictures of the far side, the side we can never see from Earth, develops the actual wet film, scans it, and radios the data back.
So, hang on, let me get this straight. In a single year, 1959, the Soviets achieved escape velocity, they impacted the moon, and they photographed the far side of it.
All in 1 year.
That is just a blistering pace.
It was a breathless pace. The Soviets were winning on every single metric. They were doing things that American scientists were still debating on chalkboards.
Which leads us to April 1961, Yuri Gagarin, Vostok 1. First human in space, first human in orbit.
And notice the American response time? A month later, May 1961, Alan Shepard launches on Freedom 7. But, and this is that crucial technical detail again, Shepard was suborbital.
He went up and came straight back down.
Exactly, like a cannonball into the Atlantic. He was in space for a matter of minutes.
Yeah.
Gagarin circled the entire world. It really highlighted just how far ahead the Soviets were in terms of raw engine power. They had the thrust to lift an entire ship into orbit. The Americans at that point just couldn't.
But the U.S. caught up fast. Though before we get to Apollo, we have to give credit where it's due for the other Soviet firsts. 1963, Valentina Tereshkova, first woman in space.
Yeah.
And 1965, Alexei Leonov, the first spacewalk.
That spacewalk, the EVA, is a story of near disaster that we often forget.
Oh.
We see the iconic footage of Leonov just floating, looking so graceful and peaceful, but in reality, his suit ballooned up in the vacuum because of the internal pressure.
Like a balloon being inflated?
Exactly. Became stiff as a statue. He said his fingers couldn't reach the tips of his gloves, and when he tried to get back into the capsule, he couldn't fit through the airlock. He was too big.
That is the stuff of nightmares, just stuck outside.
He had to make an impossible choice on the spot. He manually bled oxygen out of his suit, risking the bends and hypoxia, just to make it pliable enough to squeeze himself back inside head first. It just shows how every single one of these firsts was a genuine brush with death. We were learning the rules of spaceflight by breaking them and almost dying.
And then the moon race speaks. We get to Apollo 8 in December 1968. To me, this mission is almost as impressive as the landing itself.
Many astronauts would agree with you. Some argue it was more impressive, more daring. It was the first time human beings left low Earth orbit. They left the nest. They went into the deep dark. They were the first human eyes to ever see the Earth as a whole sphere, just hanging there in the void.
The famous Earthrise photo.
That photo changed our environmental consciousness overnight. It showed us the shocking fragility of this one place we all have to live.
And then finally, July 1969, Apollo 11, Neil Armstrong, Buzz Aldrin, first humans on another celestial body, first sample return, first launch from another world, all in one mission.
And now look at the timeline again. Sputnik was October 1957. Apollo 11 was July 1969.
Not even 12 years.
12 years.
That's the aha moment for me. 12 years. My car's 12 years old. In the lifespan of a used Honda Civic, humanity went from, can we put a little beeping ball in the sky, to let's walk around on the moon.
It's a stunning demonstration of what's possible when political will, virtually unlimited funding, and raw engineering talent are all perfectly aligned on a single goal. It was a total war economy, but applied to exploration.
But after 1969, the nature of the timeline changes, doesn't it? The political pressure just eases. The sprint is over.
It is.
Which brings us to segment 3, the golden age of robots and stations. the 1970s and 80s. This is where I feel like the big sci-fi dreams started meeting budget realities, but the robots really picked up the slack.
Exactly. We established a foothold. We stopped just racing to plant a flag and start figuring out how to stay. Salyut 1 launches in 1971, the very first space station. We realized we couldn't just visit space. We had to learn how to live there. How do you sleep? How do you eat? How do you keep the air breathable for months at a time?
And we started hitting the other planets hard. 1971, Mars 3, a Soviet probe, makes the first soft landing on Mars.
And the Venera missions to Venus. We so often forget these. Venera 7 in 1970, and especially Venera 9 in 1975.
The Venus photos just blow my mind. We have actual photographs from the surface of Venus. A planet where the surface temperature melts lead and the atmospheric pressure is like being a kilometer underwater from the mid-70s.
It was Soviet engineering at its absolute finest. They essentially built armored submarines designed to function in an oven. They would supercool them before launch and just hope they would survive long enough to transmit data. Venera 9 sent back these incredible images of a cracked, desolate landscape before it cooked, and it remains the only surface imagery we have of Venus to this day.
That's amazing. Meanwhile, the U.S. was sending probes on what they called the Grand Tour, Pioneer and Voyager.
This was just a stroke of pure cosmic luck, a planetary alignment that only happens once every 175 years.
What, all the planets lined up?
Not in a straight line, but they were arranged in a perfect curve. Jupiter, Saturn, Uranus, and Neptune were all on one side of the sun, which allowed a spacecraft to swing from one to the next using what's called a gravity assist. It steals a little bit of momentum from each planet to fling itself to the next one.
It's like cosmic slingshotting.
That's a great way to think of it. And Voyager 2, which launched in 1977, is the superstar here.
It hit the jackpot.
It did. Jupiter, Saturn, Uranus in 86, Neptune in 89. And to this day, Voyager 2 is the only human-made object to have visited those two ice giants, Uranus and Neptune. Almost everything we know about Neptune's supersonic winds or why Uranus is tilted on its side comes from that one, single flyby. It was a cursory glance, but it literally rewrote the textbooks.
And back here, closer to home, we had the shuttle, STS-1, 1981, the first reusable crewed spacecraft.
The complicated legacy, the shuttle. It was an undeniable engineering marvel. But it never quite lived up to that original promise of being cheap and easy. It was incredibly expensive and time-consuming to refurbish between flights.
But it made space seem routine, in a way.
It did, and it gave us the ability to do things we couldn't do before. Launch huge satellites like Hubble, repair them in orbit, and bring them home. And it gave us images that completely defined a generation, like Bruce McCandless in 1984.
Ah, yes, the ultimate floating in space photograph.
It is. The first untethered spacewalk. Just a man in a white suit with that manned maneuvering unit jetpack floating completely alone against the black void and the blue curve of the Earth. No cord, no safety line. It is the purest visual representation of both human vulnerability and incredible daring. If his thrusters failed, he was just gone. He would have become a distinct satellite of Earth for a few hours.
I get chills just thinking about that photo. It looks so peaceful, but the physics of that situation are absolutely terrifying. Okay, so moving into the 90s, segment 4, I'm calling this one New Eyes on the Universe.
A very fitting title. If the 80s were about going to the planets, the 90s were about seeing the broader context of our place in the cosmos.
We can start with the family portrait in 1990. Voyager 1, on its way out of the solar system, turns its camera around and snaps a picture of home.
Which gave us the pale blue dot. Earth, seen from 6 billion kilometers away, at just a tiny speck of dust suspended in a sunbeam. Carl Sagan's words. It really shifted our perspective from being conquerors of space to being the inhabitants of a very fragile island.
And then the Hubble Space Telescope launches in 1990.
And it immediately braked.
Right. It was blurry.
The primary mirror had been ground to the wrong shape by a fraction of the width of a human hair. It was a national embarrassment. But this is where the space shuttle really proved its worth. They launched a repair mission. Astronauts went up and essentially put glasses on Hubble.
It's the first telescope designed to be repaired in orbit.
And that capability saved it. And once it was fixed, it changed everything we thought we knew.
It determined the age of the universe. It showed us galaxies colliding.
It remains arguably the single most productive scientific instrument ever built by humanity.
But I think the biggest mind shift of the 90s has to be the discovery of exoplanets.
Oh, absolutely. 1992, Wolzan and Frail confirmed the first planets outside our solar system, but they're orbiting a pulsar, which is a dead star.
Yeah.
So that was weird.
Okay.
But then in 1995, we get the confirmation of 51 Pegasi b, the first exoplanet found orbiting a main sequence star. a star like our sun.
Before this moment, we thought there were probably other planets, but we didn't know.
Exactly. It moved the question from the realm of philosophy into the realm of statistics. Suddenly, the question wasn't, are there other worlds? It was, how many billions of them are there? We suddenly realized the universe is probably very, very crowded.
And while we were finding these planets light years away, we actually started driving on the one next door, 1997, Mars Pathfinder and the little Sojourner rover.
This was the big shift from static landers, the things that just sit in one spot and maybe have a scoop to mobile geology. Sojourner was only the size of a microwave oven. It looked like a little toy. But it paved the way for spirit, opportunity, curiosity, and perseverance. It proved we could wheel around on the surface of another world.
Okay, that brings us to the 2000s and 2010s, segment 5. I'm calling this one Living in Space and Landing on Small Rocks.
I like it. The living in space part is defined by one single date, November 2nd, 2000. That's when Expedition 1 arrives at the International Space Station.
And this is a stat I love telling people. Since November 2nd, 2000, there has not been a single second where every human being was on planet Earth.
That's correct. For over 25 years now, as of our recording, humanity has been permanently off-planet. We have become a spacefaring species, technically speaking. There's always someone up there floating.
That is just wild to think about. If you're 25 years old or younger listening to this, humans have been living in space for your entire existence. But let's talk about the small rocks. The precision targeting in this era just gets ridiculous.
It really does. We stopped just aiming for giant planets and started trying to intercept and land on tiny asteroids and comets moving at incredible speeds.
Yeah.
Near Shoemaker lands on the asteroid Eros in 2001. But the Japanese mission Hayabusa in 2005, that was a real thriller.
That's the one that landed on the asteroid Itokawa, right?
It did more than land. It sort of bounced down. It fired a pellet to kick up dust, collected the samples, and then, this is the critical part, it took off again. It performed an interplanetary escape without discarding any landing gear. It limped back to Earth and delivered those samples in 2010. It was a mission that was plagued by failures, engine trouble, leaks, communication blackouts. But they just refused to give up and they pulled it off.
And then Rosetta and Philae in 2014, landing on a comet.
We landed a robot the size of a washing machine on a dirty snowball that was actively venting gas and tumbling through space. The mathematics required to calculate that trajectory. It's just mind-numbing. It is a ballistics miracle.
And we can't ignore the outer solar system here either, Cassini-Huygens.
Right. In 2005, the Huygens probe separates from the main Cassini orbiter and successfully lands on Titan, Saturn's largest moon.
And it found lakes.
It did. Lakes of liquid methane and ethane. Titan is the only other world we know of that has stable bodies of liquid on its surface. It rains methane there. That methane flows into rivers that carve canyons and empty into seas. It's so familiar and yet so completely alien.
And while all this is happening inside the solar system, Voyager 1 finally does it, 2012. It leaves the heliosphere.
It entered interstellar space. It is now drifting in the vast, empty space between the stars. The first human-made object to truly leave our home system. It's our message in a bottle, floating on a cosmic ocean.
Okay, now we're getting to the modern era. Segment SOS, the new space age. From 2015 to, well, basically the present day.
The defining characteristics of this era are commercialization and reusability. And the pivotal year for that is absolutely 2015.
It was the year of the landing wars.
It really was. In November 2015, you had Blue Origin propulsively land their New Shepard booster after a suborbital flight. Then, just a month later, in December, SpaceX lands their Falcon 9 orbital-class booster.
I remember watching that Falcon 9 landing live. It looked like footage being played in reverse. It just didn't seem real. This pencil falling out of the night sky, lighting its engine at the last second, and just landing perfectly upright on a concrete pad.
That was the moment the economics of spaceflight fundamentally changed. If you can reuse the most expensive part of the rocket, the cost of access to space plummets. Before this, every rocket was like an airplane that you threw away after a single flight. 2015 fulfilled the dreams of those early 20th century pioneers like Tsiolkovsky, who knew that throwaway hardware was never going to be sustainable.
And that just opened the floodgates. We've also seen this huge ramp up in Mars technology since then, the Ingenuity helicopter in 2021.
Our Wright brothers moment on another planet. The first powered aerodynamic flight on another world. It proved you can generate lift in an atmosphere that's only 1% as dense as Earth's. And on that same Perseverance rover mission, you had the MOXI experiment.
Which made oxygen.
It successfully produced oxygen from the Martian carbon dioxide atmosphere, in situ resource utilization.
So we aren't just looking anymore, we're practicing living there. And we are also practicing, well, defending here, DART.
September 2022, the double asteroid redirection test. We intentionally slammed a spacecraft into the small asteroid moonlet Dimorphos just to see if we could change its orbit.
And we did.
We did. We shortened its orbit around its parent asteroid by 32 minutes. It was a huge success. It was the first time humanity has ever measurably altered the natural motion of a celestial body. We moved a rock in space. And that implies that we are no longer just passive victims of cosmic billiards. If a dangerous rock is coming for us one day, we now know, theoretically, we can play the game.
And then there's the moon. Suddenly everyone is going back to the moon.
But not to the same places. Not to the equatorial regions where Apollo went. The action now is at the poles, where there's water ice, and on the far side. China's China 4 made the first ever soft landing on the far side in 2019.
But first,
India's Chandrayaan 3 made the first landing near the lunar South Pole in 2023.
another first.
And then Chang'e 6 returned the first ever samples from the far side in June of 2024.
Which brings us to, basically now, Segment 7, the recent past. Since we're recording this in January 2026, we have to talk about the things that happened just last year and late 2024, because things have gotten sci-fi real.
We have to talk about October 13th, 2024, Starship Flight 5.
The chopsticks.
SpaceX caught a super heavy booster, a building-sized rocket stage out of the air using the launch tower's own mechanical arms.
I still watch the replay of that. It looks fake. It looks like bad CGI from a movie, but it's real physics. The precision required to have that massive steel cylinder hover perfectly and let itself be caught by these little pins.
It's the key to rapid reusability on a massive scale. It signifies that you can turn the rocket into something more like an airplane. You refuel it, you restack the ship on top, and you fly again within hours or days, remove the need for landing legs, it saves weight. It was this enormous engineering gamble that actually paid off. It was the moment where the scale of spaceflight really shifted from the idea of a capsule to the idea of a ship.
And then, almost a year ago now for us, April 1st, 2025. The Fram-2 mission.
This was a SpaceX Dragon mission, but a very significant one. It was the first crewed space flight to ever enter a polar orbit around Earth.
Okay, so why is a polar orbit such a big deal? I mean, we've been orbiting for decades.
It's all about energy. When you launch east from, say, Florida, along the equator, you get a free speed boost from the Earth's natural rotation. It's like stepping onto a moving walkway at the airport.
Okay, got it.
But if you want to launch north or south over the poles, you lose that boost. In fact, you have to fight against it. You have to muscle your way into that orbit with pure rocket power. It costs way more fuel and requires incredibly precise timing.
So why do it? What's the point?
To see the parts of the Earth that we usually miss, the Arctic and the Antarctic. What Fram-2 showed was that private astronauts, not just government employees from NASA or Roscosmos, are now doing complex, high-energy orbital mechanics. They aren't just taking joyrides up and down anymore. They are explorers doing real scientific observation over the poles. It marks a new maturity of the commercial sector.
So what does this all mean? We've gone from Tsiolkovsky scribbling equations in a Russian log cabin to catching rocket boosters with giant chopsticks and tourists flying over Antarctica from space.
Well, if you look at the whole arc, I think you see a clear transition from observation to exploration, and now to utilization.
Unpack that for me.
Galileo observed. He just watched the show from afar. Apollo and the Voyager probes explored. They went there, they poked around, they took pictures. But now, with an experiment like MOXIE making oxygen on Mars, with DART moving asteroids, with Starship promising to carry massive tonnage to orbit, we are beginning to utilize space. We're starting to change the environment to suit our needs. We are taking the resources of the cosmos and beginning to bend them to human will.
We've moved from just looking at the stars to actually grabbing pieces of them.
Exactly. We have had an uninterrupted human presence in space since the year 2000. We have private missions going into complex polar orbits. We have multiple space agencies with concrete plans for bases at the lunar South Pole to mine water ice.
It makes me think, are we done with the exploration phase? Is that over?
I wouldn't say it's done, but we are definitely overlapping into something new. The frontier is closing in a sense, and the settlement is beginning. We're living in the transition period that historians centuries from now will look back on as the moment humanity truly, finally, left the cradle.
So here's my final thought for you, for everyone to chew on. With everything we've just laid out, the permanent habitation on the ISS, the oxygen generation on another planet, the reusable heavy lift, the asteroid deflection, at what point do we stop calling it space exploration and start calling it human migration?
That is the question of this century, and I think the answer is sooner than most of us think.
Something to think about next time you look up. Keep looking up.